Merry Christmas. So we got another request from Shiva. Is this problem, right? So we are going to discuss this problem to celebrate Christmas, alright? So let's begin. As always, we introduce this problem by explaining the example, right? In the input, we have a 5 here. So 5 is the number of columns in the histogram, right? 1, 2, 3, 4, 5. And the numbers are following the first number is height of each column, right? 3, 2, 2, 2, 1, right? So what's the output? The output is the maximum number of shapes we can put into the histogram, and we can choose one of 2 shapes to put into this histogram. One is like this, right? It's 2 multiplied by 1, right? Like this one. And another shape is like this, right? 2 domino shapes, right? And in this case, the maximum number of shapes we can put it into the histogram is 4. We can put it in this way, right? There are 4 of them. And we also can put it in this way. There are 4 of them, right? So in this case, we output 4. There is no chance we can put 5 domino shapes into this histogram, right? So that is the correct answer. So how do we solve this problem? So the first step to solve this problem is coloring, right? We put 2 colors into the histogram. As we can say, we need to make sure that there are no 2 colors sit next to each other, right? If we put another red here, these 2 red sit next to each other, so that's wrong. We need to make sure that doesn't happen. So in this case, whenever we put a domino shape into this histogram, like this one, we can be sure that the domino will cover 2 different colors, blue and red, right? For example, we can also put it here, so it also covers 2 colors, blue and red. We put it here, 2 colors. We put it here, 2 colors, right? So in this way, we can transform the problem into a bipartite problem, right? So all we need to do is to pair up the red and blue and make sure we can find as many as pairs as possible. So that's a standard bipartite problem, right? So we have 2 parties. One is red and one is blue. And we have to pair. We have to pair between these 2 parties. And we need to make sure that we got as many pairs as possible, right? That's a standard bipartite problem. And this bipartite problem is very special, right? We can draw a conclusion that the maximum number of pairs equals to the number of smaller column in this case, blue has 4 nodes, right? And the red has 1, 2, 3, 4, 5, 6 nodes. So blue is the smaller one, right? So blue is the smaller color, and it has 4 nodes. So we can be sure that the maximum number of pairs is 4. So why does the statement hold itself, right? So we are going to prove it, right? So in order to prove that the maximum number of pairs equals the number of the smaller color, we can assume if there is if the maximum number of pairs is less than the number of smaller color, right? We can find a blue that does not pair to a red, right? So in this case, we can also find a red that doesn't connected to any blue, right? Because the number of red nodes is bigger than the number of blue nodes, so we can be sure to find a red node that does not connect to a blue node, right? Let's say these 2 nodes are not connected to any opposite colors, right? So in this case, we can always find a argument path to these 2 nodes. What is the argument path? So let's put the graph here to better illustrate the definition of argument path, right? So let's say in this case, we already have a pair here, and a pair here, a pair here, and this blue does not connect to a red, and this red does not connect to a blue. So argument path is that we got a non-pair blue here, right? And we got a non-paired red here, right? And we got 2 pairs in between, right? This pair equals this pair, and this pair equals this pair, right? So in this graph, we have 2 pairs. If we switch the connection state of each of all of the neighborings, like there is no connection between these 2 nodes, so we flip it, we create a new connection, and there is a connection between these 2 nodes, so we flip it, and there is no connection here, right? So we flip all of the connections, we can get a new graph, and this new graph has 1 more pair than the old graph. So we got a argument path here. So argument path is just a fancy word saying that through this path we can get 1 more pair, right? Pair argument by 1. That's the argument path, right? So that we can be sure that for each two non-paired nodes, we can always find an argument path between them, and in this way we can get one more pair, so that the non-paired two nodes will not exist anymore, right? So in this way, we proved that the maximal number of pairs equals the number of smaller columns, right? So the code will be very simple, right? So let's remove all the stuffs and read the code, right? The code is really simple. So we have a red counter and a blue counter, and we don't actually need the answer, right? So we read in the number of columns and read in all of the height of the columns, and if we are at the all the columns, we draw a red first, right? Just as we did before, we draw a red first, then a blue, then a red. So the number of red nodes is the height plus 1, then divided by 2, right? So the blue color is just the number of the height divided by 2, right? So in the even columns is vice versa, right? So the blue node is either equal to the red node or bigger than the red nodes by 1, right? After we get the number of blue nodes and the red nodes in the graph, we can just print out the smaller one. So that's it. Hope that helps. Thank you for watching.